Hello and welcome to lecture 58. In last lecture, we were discussing about the construction of propfan. We also have discussed about the thermal cycle analysis of this propfan configuration, as well as we have also discussed in terms of calculation of performance parameter for such configuration. So, let us take a tutorial for that. We have unducted fan, that is what is fitted with the aircraft which is flying at 200 meter per second at altitude of 6 kilometer, where temperature is 249 Kelvin, pressure is 47.18 kilopascal. Be careful, this speed it is at that particular altitude. So, we cannot straightway take this in terms of Mach number. If we are taking that Mach number, it should be with this temperature. It says the engine is comprising of 3 spool configuration. The pressure spools are composed of LP compressor driven by LP turbine, HP compressor driven by HP turbine, and unducted fan is driven by say free power turbine. So, here you can say we are having say HP turbine, we are having say LP turbine, and this is what we say as a free turbine configuration. So, maximum cycle temperature is 1450 Kelvin. The calorific value or the fuel heating value is 43,000 kilojoule per kg. The information available are say mass flow rate is 40 kg per second, LP compressor pressure ratio 3.15, HP compressor pressure ratio is 5.62, pressure ratio of unducted fan is 1.25. The isentropic efficiency for the duct it is 0.9. There will be drop of pressure by 6%. Say LP compressor efficiency is 85%, HP compressor efficiency is 86%, burner efficiency is 96.5, LP turbine efficiency is 91%, HP turbine efficiency is 93%. Free turbine efficiency is 92%, nozzle efficiency is 96%, efficiency of unducted fan is 82.5. It says the split factor is 0.85, Cp value for air is 1005 kilojoule per kg, as well as the Cp value for say hot gas is 1.148 kilojoule per kg. We need to calculate what will be the bypass ratio, ratio of the thrust generated by unducted fan and the nozzle, and total equivalent horsepower. That is what is required to be calculated for this configuration. So, best practice, as we have discussed for almost all cycles, very first thing we need to do is draw a line diagram which is representative of the configuration which is given. Here in this case it says my LP compressor is driven by LP turbine, HP compressor is driven by HP turbine. So, we can say for the core engine we are having this as a 2 spool configuration. It also says power turbine, it is used to rotate the unducted fans. So, here in this case this is what is our free turbine. Now, no information as such is available whether it is having nozzle or not, but still let us try to put that, say we have nozzle at the exit. Okay. Now, let us try to understand how do we solve this numerical. So, what all information is given to us or known to us, we will be starting with that. For intake, we have information about say flight speed, altitude, pressure, temperature and diffuser efficiency, from which we can calculate what will be the temperature and the pressure at the exit of the intake. The next component we have is our LP compressor. For LP compressor, the efficiency is given, pressure ratio is given. So, based on that we can calculate what will be the outlet pressure and outlet temperature from the LP compressor. Next we have is our HP compressor. For HP compressor also the isentropic efficiency and the pressure ratio that is given. So, based on known pressure and temperature at the entry, we can calculate what will be the exit pressure and exit temperature from the HP compressor. We have our component, it is combustion chamber, and for that combustion chamber burner efficiency or combustion chamber efficiency is given, drop of pressure is given, maximum turbine entry temperature is known to us. So, we can calculate what will be the pressure and what will be the amount of fuel, that is what is required to raise that temperature to turbine entry temperature. We have our component, it is say HP turbine. We know this HP turbine, it is used to rotate the HP compressor. The information given, it is in terms of isentropic efficiency, my entry temperature, that is what is known. So, based on our work balance, we can calculate what will be the pressure and temperature at the exit of the HP turbine. Similarly, we have component, it is LP turbine. This LP turbine, it is used to rotate the LP compressor. The information given for this LP turbine is the isentropic efficiency. Based on entry pressure and entry temperature, based on work balance, we can calculate what will be the exit pressure and exit temperature from the LP turbine. Now, here in this case, this is somewhat different in terms of the solution. So, we will be configuring first as say unducted fan, and for that unducted fan, the isentropic efficiency is given, the pressure ratio is given. So, based on our entry condition, we can calculate what will be the outlet pressure, outlet static temperature, and what will be the velocity, exit velocity from the unducted fan. As we have discussed, we have free turbine and nozzle. So, combinedly we are putting here, and for this we are given with the split factor. We are also having the information in terms of the isentropic efficiency of the free turbine. So, based on that, we can calculate what will be the static temperature, what will be the static temperature at the exit of power turbine, what will be the exit temperature at the nozzle, and based on that we can calculate what will be the exit velocity from the nozzle. So, once we have all this information, based on that we can calculate the performance parameter of this engine. Okay. So, with this background, I am sure you are able to understand how do we proceed with. So, this is also one of the way to make the solution for the cycle analysis. So, let us try to understand this. So, here in this case, let us say we have our first component, it is say intake, and for that intake we have information about the flight velocity, it is 200 meter per second. It is flying at 6 kilometer altitude, where pressure and temperature they are also known to us. So, based on that we can calculate our flight Mach number, that is 0.632. Once we have information about the flight condition, we know we can correlate our say diffuser efficiency in terms of pressure. So, this outlet pressure at the intake, that is what is given in terms of say diffuser efficiency. For the current numerical, the diffuser efficiency is given, it is 0.92. Let us put that value. If we are putting that value, the outlet pressure from this intake, it is coming to be 60.16 kilopascal. Now, let us try to calculate what will be the exit temperature. So, we know that exit temperature can be calculated based on the isentropic relation. Since Mach number is known to us, we can calculate the outlet temperature, and this outlet temperature is coming to be 268.89 Kelvin. Now, let us try to look at the component we have is LP compressor. For LP compressor, we have information in terms of pressure ratio, it is 3.15, and the isentropic efficiency is given 85%. So, let us try to calculate the outlet pressure based on the pressure ratio. We have our inlet pressure to be 16.16. Based on that, we can calculate the outlet pressure, that is 189.5 kilopascal. We know we can correlate our temperature with the pressure ratio as well as the efficiency. So, let us try to put that equation. So, if we have information about say pressure ratio and efficiency, we can calculate our outlet temperature from the LP compressor, and this temperature is coming to be 391.61 Kelvin. Be careful in terms of unit. Now, let us look at the next component what we have. Our next component is HP compressor. For HP compressor also we have information about the pressure ratio, it is 5.62. The efficiency is given, it is 86%. So, based on pressure ratio we can calculate our outlet pressure, that is 1064.99 kilopascal. And temperature, as we have discussed for LP compressor, temperature we can correlate with the pressure ratio as well as the isentropic efficiency. For the HP compressor, if we put this number by T04 or the temperature at the exit of HP compressor is coming to be 681.95 Kelvin. So, let us look at the component we have is a combustion chamber, and for this combustion chamber we are given with the drop of pressure by 6%. So, that is what will be giving us the outlet pressure. That outlet pressure is coming to be 1001 kilopascal. Now, in order to raise the temperature as per our expectation in terms of 40-50 Kelvin, we need to add the fuel in combustion chamber. So, in order to calculate the amount of fuel what we need to add, or we can say the fuel air ratio, that can be calculated based on our say energy balance for the combustion chamber. Here in this case we can write down in terms of the equation here. Be careful what all units you are taking, you need to maintain the uniformity in terms of units. Suppose say Cp value you are taking in terms of joule, then your calorific value also should be taken in joule. Suppose you are taking in kilojoule, then your calorific value also should be in kilojoule per kg unit. Here if we are calculating the fuel air ratio, that is what is coming 0.0245. Okay. Now, let us try to look at the component we have, it is our HP turbine, and for this HP turbine we have information about the entry temperature and entry pressure. In order to calculate the outlet temperature and outlet pressure, we must have the information what is the purpose of this turbine. So, here in this case my HP turbine, it is used to rotate the HP compressor. So, if we are writing our work balance, then based on that work balance we can calculate the outlet temperature of the HP turbine, and that temperature is coming 1021.9 Kelvin. Okay. Now, in order to calculate what will be the outlet total pressure, we have our information in terms of what is our say efficiency, isentropic efficiency. This isentropic efficiency we can correlate in terms of pressure ratio, or we can say expansion ratio, and that is in the form of temperature. So, let us try to put that equation. If we are putting that, the outlet pressure from the HP turbine, it is coming 441.12 kilopascal. Now, this will be the inlet condition for our next stage, that is what is say our LP turbine. Say for LP turbine, in line to what all we have done for HP turbine, we can say here LP turbine it is used to rotate only LP compressor. So, if we will be writing our work balance equation, we can calculate what will be the outlet temperature from the LP turbine, and this LP turbine temperature is coming 1097.03 Kelvin. Now, in order to calculate what will be the outlet pressure, we can correlate our expansion ratio or the pressure ratio in terms of temperature as well as our isentropic efficiency for the LP turbine. The isentropic efficiency for the LP turbine, it is given 91%. So, let us put that number, and if we are calculating, the pressure is coming to be 638 kilopascal. Now, let us try to analyze the component, that is what is a unducted fan, and for that unducted fan the information available with us is in terms of what is the pressure ratio of that. We have information about the entry condition. So, very first thing we need to calculate it is what will be my total pressure and total temperature at the entry of my unducted fan, and what will be the outlet pressure and outlet temperature from the unducted fan. So, let us try to analyze that part. Here in this case we can say my temperature at the entry, that will be 268.89 Kelvin, and the pressure that can be calculated based on the Mach number, and that value is coming 61.74 kilopascal. Now, let us try to look at what will be the outlet pressure from this fan. Since my pressure ratio is given 1.25, so the outlet pressure is 77.18 kilopascal. Okay. Now, here in this case we are also interested in what will be the outlet temperature. This outlet temperature can be calculated based on what is our isentropic efficiency of the unducted fan and what is our pressure ratio for the unducted fan. So, if we are putting this number, the total outlet temperature from the unducted fan, that is coming to be 290.35 Kelvin. Now, this is what is helpful to us in order to calculate what will be the static temperature at the exit of unducted fan based on our isentropic correlation. So, if we are putting this number, say the outlet static temperature is coming to be 252.26 Kelvin. Now, just realize what is the use of this number. This static temperature, that is what is used for the calculation of what will be the exit velocity from the unducted fan. So, this exit velocity that can be written in terms of this equation. So, if we have the information, we can say it is 2 Cp delta H, and this delta H we are writing in terms of say temperature. So, here the exit velocity is coming to be 276.69 meter per second. Okay. Now, let us try to analyze the component, that is free turbine and the nozzle. As we have discussed, here in this case the process 7 to 8, that is what is representing my free turbine configuration, and from 8 to 9, that is what will be representing our say nozzle configuration. Here for this numerical, the split factor it is given to us. So, we will try to calculate first what will be delta H, ideal delta H. That is what we can say, we are assuming the process, that is what is happening in free turbine and nozzle, that is what is isentropic process. So, let us try to analyze that part. Here in this case, the temperature at the exit, that is what is say 9 S, that can be calculated based on our isentropic correlation. This isentropic temperature is coming to be 574.36 Kelvin. This will be the static temperature at the exit of combined turbine as well as nozzle. Now, we have information in terms of say work developed or the work required, that is what can be written in terms of say efficiency of the free turbine into alpha into delta H. If we are putting this delta H can be represented as a T07 minus T09 S, and free turbine work, that is what we are writing in terms of T07 minus T08. Now, here in this case we can calculate what will be the outlet temperature from the free turbine. So, if we put all these numbers, T08 it is coming 688.3 Kelvin. So, here in this case we can say we have information about this temperature now. Now, what is our next requirement? We need to have what will be the pressure, because P08 it is the exit pressure from the free turbine and that will be the entry pressure from the nozzle. So, let us try to calculate that value. Now, for this free turbine, based on our isentropic correlation, we can calculate what will be the isentropic temperature, that is T08 S. This T08 S, that is what is coming as 652.76 Kelvin. Now, there is a reason for the calculation, because we want to have what will be the outlet pressure. That outlet pressure can be correlated in terms of say isentropic correlation. That is what is given by this ratio. It is P07 by P08. It is given by T07 by T08s to the power gamma over gamma minus 1, because this process from 7 to 8s, that is what is isentropic process. So, if we have this information, we can calculate what will be the pressure P08. So, let us try to calculate that pressure. If we put all these numbers, the P08 value is coming to be 78.76 kilopascal. Since here in this case this alpha value is known to us, that is the reason why it makes life easy in terms of calculation. Maybe in some instance you may need to assume the value of alpha. Based on the iteration, you may need to come up with the solution. We have discussed this thing in our turboprop engine configuration. So, just revisit again if you have any confusion. Now, the process here is in terms of now nozzle. We need to calculate what will be the outlet pressure from this nozzle, and for that very first thing we need to do is to calculate what will be the critical pressure or critical pressure ratio, because that is what will be helping us in order to understand whether the nozzle is choked or unchoked. So, if that is the case, we have information in terms of say nozzle efficiency, that is 96%, gamma value is 1.33. So, if we are calculating that, the pressure is coming to be 41.4 kilopascal, and that pressure, that is what is lower than that of our atmospheric pressure. It is say 47.18. So, you can understand this nozzle, that is what is unchoked nozzle. If this is the unchoked nozzle, then we can say my outlet pressure, that is what will be my atmospheric pressure. Now, if that is the case, we can put P9 equal to P infinity, it is 47.18 kilopascal. Now, our requirement, it is to calculate what will be the exit velocity. Here, rather putting few more steps, we have kept the relation straightway in terms of pressure ratio. Let us put the numbers. Here in this case, the Cp value, nozzle efficiency, T08, the pressure ratio, that is what is known to us. So, that says the exit velocity is coming to be 425.6 meter per second. You can understand this value is on higher side. So, you can say we will be having the contribution in terms of thrust generation by our core engine nozzle. Okay. Once we have all this information, we need to calculate our performance parameter. In terms of performance parameter, very first we will be calculating the thrust, that is what is generated by the nozzle, or we can say nozzle thrust, that is given by m dot core into 1 plus f V9 minus V infinity. This V9 value, that is what we have calculated. So, let us put these numbers. If we are putting this value, the thrust generation by the nozzle, it is coming to be 9441 Newton. Let us try to look at what will be the thrust generated by the fan. This fan, we can say it is given by beta into m dot core, exit velocity minus free stream velocity. So, here in this case we are not having the information about beta, that is what is the bypass ratio. So, let us try to calculate that bypass ratio first. So, how do we calculate the bypass ratio? We can say the free turbine, what all work it is been generated by the free turbine, that is what is used to rotate these rotors. So, let us do the work balance for that. It says the work that will be generated by the free turbine, that is what will be equal to work required by the unducted fan. And if we are writing this equation, it will be giving us the value of bypass ratio, and this bypass ratio is coming to be 22.28. Okay. So, in compared to the turbofan engine, if we are looking at this number is on higher side, but when we are comparing with this turboprop engine, this is on the lower side. We have seen the difference between say turboprop engine and propfan engine. So, do not get confused with these configurations. Now, once we have this beta value, so let us try to put these values here. So, for the unducted fan, the thrust generated, that is what can be calculated based on beta into m dot core minus into bracket we have exit velocity minus free stream velocity. It says the thrust generated, it is given by 68.34 kilonewton. So, huge amount of thrust, that is what is being generated by the unducted fan, and here there is a contribution by the core engine also. So, my total thrust generation, that is what is given by 77.78 kilonewton. Okay. We want to calculate what is the thrust ratio. It is basically a proportion. So, many times for the engine design, people they are defining this, or they will say the expected thrust ratio for this engine. So, we should not get confused in terms of terminology. This thrust ratio, as we have discussed, it is a thrust generated by the unducted fan divided by thrust generated by the core engine, and this is coming in the range of 7.23. Okay. So, we can say my unducted fan is generating 7 times thrust compared to my say core engine. Okay. Now, we want to calculate the other parameter is in terms of power, because we are discussing the power turbine configuration. So, we are also interested in calculation of power, that is what will be generated by both nozzle as well as the power required to run the unducted fan. So, for that nozzle power, that is what can be written as say T into V infinity. This thrust value we have calculated, it is 9441 into 200, and it says the power it is around say 1,888.2 kilowatt. When we are calculating the power for the unducted fan, that is what is coming to be 13669.2 kilowatt. So, you can say that is what is nearly 13.66 megawatt. It is a huge power. Similarly, the power generated by the nozzle, that is also 1.88 megawatt. So, just try to understand the numbers. Okay. Suppose if we are calculating the equivalent power, we can say that is what is coming to be 15.55 megawatt, or we can say that is what is given as 20862 HP horsepower. Now, once we have all this information, we will try to calculate what will be the propulsive efficiency. So, if you recall, in last lecture we have discussed, we are interested in the total thrust. That is the reason why it is the thrust which is generated by the core engine plus the thrust, that is what is generated by unducted fan. In denominator we are having this thrust value plus this kinetic energy value. If we will be putting all this number, then we will be coming up with value. Say here in this case, propulsive efficiency is coming to be 80.96% for this engine. So, as we have discussed, these engines they are having high propulsive efficiency. So, our target it is to achieve higher propulsive efficiency by incorporating the bypass ratio, and here in this case that is what is being proven with. Now, let us try to move towards the next calculation, that is what is in terms of thermal efficiency. So, for thermal efficiency in the denominator we will be having MF into CV, and if we are putting all these values, the thermal efficiency of this engine it is coming to be 45.61%. So, this thermal efficiency also is on higher side compared to what all engines we have discussed with. Okay. Now, let us try to look at the overall efficiency. This overall efficiency we can say it is propulsive efficiency into thermal efficiency, and that is what is coming to be 36.92%. So, if you try to compare what all engines we have discussed up till now, this engine that is what is having higher overall efficiency, and that is what is the major attraction for say use for the future engines. just try to realize these numbers. So, here in this case, suppose say if I want to calculate the thrust specific fuel consumption, that is what is given by m dot f divided by total thrust, and if we are calculating that, it says my thrust specific fuel consumption is coming to be 12.6 gram per kilonewton second. Similarly, for the engine people, they are more interested in equivalent specific fuel consumption, because they are discussing more in terms of equivalent shaft power. So, if we are putting these values, then here in this case we need to go with the conversion part from kg to say pound, and here this is what is in terms of per second to say per hour configuration. So, it says equivalent specific fuel consumption, that is what is coming to be 0.3728 pounds per HP hour. So, there are different units, based on that people they are trying to analyze say SI unit, MKS unit. So, all those kind of configurations we have. So, I am sure this is what will be giving you overall idea in terms of calculation of the performance parameter. So, let us try to come to the conclusion part here. So, for this engine, unducted fan engine, that is what is flying at 200 meter per second at altitude of 6 kilometer, where the pressure and temperature is given. For that we have done calculation for the total thrust, that is what is coming 77.78 kilonewton. Then we have found the thrust ratio, it is 7.23. We have also calculated the equivalent power, we have calculated propulsive efficiency, thermal efficiency, overall efficiency, thrust specific fuel consumption, equivalent specific fuel consumption for this engine configuration. So, here we are stopping with. I am sure you are having the clear cut idea how the cycle analysis for prop engines they are different from what all we have discussed up till now. Now, in next lecture we will be starting with making the background for our next week discussion for the component matching. So, we will be discussing about the subsonic aircraft flight envelope. We will be discussing about how do we go with the component matching, because that is what is of major interest, and that is what is say limited in open literature for the discussion. So, next week we will be having very good discussion on component matching, and in overall if you will try to understand, then that will give the clear cut idea how the engine that is what is been configured with. So, stay connected with. In next lecture we will be discussing the fundamental requirement for our week 12, and in week 12 it will be very good discussion in terms of different component matchings. That is what is required for what all engines we have discussed up till now. So, thank you very much.